Our talk today is by Noémie Le Carrer, a PhD student at the Institute for Risk and Uncertainty in her final year, and she'll be talking about challenges facing probabilistic interpretations of ensemble weather forecasting. So, Noémie, take it away.
Okay. So I will make a presentation to introduce you the concept of ensemble predictions in weather forecasting and the new methodologies that I developed to interpret these predictions. So maybe just a few words about the context, because I'm not a weather person initially, so not a weather specialist, but I bumped into this problem because I was working on sea level predictions to optimize maritime shipping subject to uncertain sea levels. And so I was initially working with type predictions, and I compared the actual sea level with the weather forcing compared to the type predictions, and I modeled the difference. But then I realized there were more predictions. And so I started to read more about it and can you hear me? Can you hear me?
You cut out briefly for like a second, but you're fine.
Okay, otherwise. Because I see my connection is unstable, so I was a bit. So I bumped into this problem and started to read more about it, and I got very interested in it. So I decided to try to find to suggest a solution. So here it is. So we will. Here is a summary as a table of contents. So I will introduce first the motivation for interpreting ensemble forecast in a different way than what is currently done. And because it's a possibilistic interpretation, we will, and not everybody is familiar with possibility theory, we will present a little bit the basics of possibility theory. And then I will introduce the big framework, the methodological framework, and then show the results and conclude. So let's start with weather predictions, with ensemble prediction systems, as we call them. So when you want to predict the weather and to assess the predictability of the weather, so the level of risk around, the level of certainty around your predictions, the confidence you can have in your predictions, you face a big problem with the weather dynamics. It's the weather dynamics, the atmospheric dynamics, is very sensitive to initial conditions. But the global models, the global numerical models that are run to make weather predictions have a limited grid resolution, so a few kilometers on the horizontal level and a few dozen kilometers on the vertical levels, depending on the resolution, but still it's quite a limited grid resolution, so you cannot have perfect initial conditions. And second, you have another source of error, which is the model error, especially the closure problem, because you cannot model all the physics of your atmospheric systems, especially in particular because of the limit grid resolution. So at some point you are obliged to close the equations to make some parameterization to account for local humidity and so on. So operationally, what do you do then? In the past, people try to make the best deterministic predictions, so to have the most accurate physical model and to have the most accurate initial predictions, initial observations, initial conditions of your systems. So the temperature, the wind here and there around the globe, and then you run the best accurate model you have, and you get if you have a very good time resolution, you get the best prediction you can have, the best deterministic prediction you can have. But in the 2000s, at the beginning of this century, because of more available computer power, especially, they started to say, okay, we can maybe run several times the model with slightly perturbed initial conditions and pretend then we have a sample of the possible future scenarios a sampling of the possible future scenario and interpret it in a Monte Carlo way. So that's just the idea. You sample m perturbed initial conditions around your best observation of the current system, of the current atmospheric system. And then you run forward the model. This model can also be stochastically parameterized to account for model error. And then at the end, so that's what you can see on the plots, you get a set of M ensemble predictions. So in the plots, you have the lead time, so how long ahead do you predict, and on the y-axis, the variable of interest. So the black line represents one of these ensemble predictions. Here, I think you have 24. The red line is the truth, so the true trajectory of the system, and the blue line is the best model prediction, so the traditional deterministic prediction. Because also this ensemble prediction, so this M run of the models, are run at a slightly lower time resolution, so they are a bit imperfect with respect to time step. So that's what you have. What do you do with it? When this methodology started to develop, as I said, the idea was to interpret it in a Monte Carlo way. So there was a shift in paradigm where the weather became, from deterministic, it became probabilistic. So you started to have a lot of papers with shifting paradigms, the probabilistic Earth system, probabilistic weather, and so on. And the global idea was, to make it simple, to use the ensemble prediction as a proxy of the true distribution, of the future weather. So basically, to use its standard deviation to quantify the standard deviation of your prediction, to use its mean as a best estimate of the future weather, for instance. So to use a characteristic of a PDF that you would fit on the ensemble predictions as describing the knowledge of the future system of the future state of the atmosphere. So the first limitation is that this ensemble prediction paradigm assumes that the model error is low, which is not. It assumes that the model error is low, and the error comes mostly from the initial conditions, from the error on the initial conditions. But in practice, this is not true. So you have a nice how do you say? I can miss English, like a nice picture to show it. So basically, if your model error is important, so that's the green thing, the forecast uncertainty with model bias. So your ensemble prediction are the blue lines. So you get them here, and so you would deduce from them that okay, your solution is in the blue area. But if it's only if the uncertainty comes from the initial conditions, the uncertainty on the initial conditions. If you have model error as well, and important model error, then maybe you can arrive here and you have no idea about it. So that's the first limitation. Second, the we are here, the I-dimensionality of the system. So when you run a global weather model, you have one vector of the state of the system is millions of dimensions because it's over this grid, like vertical grid and horizontal grid all over the Earth. It's global models. So how do you sample that vectors to run in practice just 10 to 50 ensemble predictions, 10 to 50 perturbed initial conditions, and that will lead to 10 to 50 predictions. So how do you choose 50 of them when you have a system with million dimensions? And you are limited in terms of computational budget, of course. So some techniques have been developed for instance, they will choose the initial perturbation so that they are the fastest growing initial perturbation. So that's a way to select the perturbations that will lead to actually slightly different possible weather patterns. So it's good to it's a good way to sample the possible future scenario for the weather, but you cannot say anymore that your M samples are representative of the actual probability of having this one or this one, because the sampling is biased initially. Another problem is the extreme events, because extreme events are born from a nonlinear interaction at small scales. So by definition of the ensemble prediction methodology, you cannot have in your set of M predictions more than a couple of predictions that will predict an extreme event, because if you perturbate initially the initial conditions, because the extreme events are born from very small nonlinear interactions at very small scales, in any case, the initial perturbation will prevent from reproducing several extreme events in your predictions, in your ensemble prediction. So that's another big limitation. And the final one is that if you fit a PDF on your M ensemble prediction, the figures, like the probabilities you get for any event on your X square, I mean on the variable of interest. So these probabilities are not really probabilities because they are not actionable. If you use them to bet, you are going to lose for sure on the long term. So they don't represent the real probabilities of the system, the real probabilities of observing this or this event. Donc, yeah, sorry, it was French. So, because of all these problems, especially because we cannot interpret like the probabilities derived directly from the ensemble members as probabilities, a range of methodologies, so-called post-processing or calibration, have been developed to calibrate, to probabilistically calibrate these figures, these probabilities. So basically make them meaningful so that they are really probabilities. So you have parametric, non-parametric methods, methods that are more fitted for extreme events, methods that are fitted for that are more generic. So over the years, a lot of methods have been developed. The problem is that if this generic post-processing methodology improves the ensemble skills, so the prediction skills for like common events, and they extend the skillful prediction or reason for these events. However, they tend to deteriorate the performance for extreme events because most of them are based on the optimization of parameters. They are parametric post-processing approach. So they optimize parameters over a big training set, but this training set contains mostly common events, so they will optimize it for common events and not for extreme events. So that's one of the examples. And the extreme event case, so like providing probabilistically calibrated probabilities derived from ensemble predictions for the prediction of extreme events and probabilities that are skilled. So this problem must be addressed by specific non-global methodologies, so very adaptable, flexible. And for all these reasons, given that a lot of tailored post-processing steps are necessary to get more or less, because it's not perfect, the results are not perfect, so more or less meaningful probabilities, echoing a paper written in 2008, we wonder whether the probability distribution is the best representation of the valuable information contained in an ensemble prediction system, so in an ensemble of prediction. And we bumped into a possibility theory, which is a quote, a weaker theory than probability, relevant in non-probabilistic settings where additivity no longer makes sense. And so we wonder if this possibility theory doesn't represent new opportunities in a context where actually the conceptual and practical limitations restrict the applicability of a density-based, so probability density functions, interpretation of ensemble predictions. And so we will investigate the benefits of first, using a framework based on possibility theory for extracting the valuable information contained in an ensemble prediction system. And second, combining it, we will show how we can combine it with the insight about the local dynamics of the system of interest. So I will start, I'll just check time. Okay, so I will start with a few generalities about possibility theory to make everybody more familiar if you are not with it. So possibility theory was developed from physicist theory a few decades ago to handle incomplete knowledge and to represent ignorance, especially. So if you have an illustration here of a possibility distribution function or possibility membership function. So pi of S. So S represents the state of your system, and the pi of S will take values between 0 and 1 and represent the state of knowledge. The whole pi of S represents the state of knowledge about the state of the system. So locally, if pi of S equals 0, it means that the state is rejected. It's not possible at all. If it's equal to 1, the state is absolutely possible, but we don't know more yet, just with this indication. And the intermediate values are used to represent the incomplete knowledge on the system state, and we will see how to interpret that. So, question, for instance, does the event A, so S belonging to a subset of the possibles here, happens? So to answer that, based on the information encoded in the possibility distribution function, we will compute the degrees of the measures possibility and necessity. So the possibility here is the maximum of pi over the subset of interest, and it explains to what extent A, the event of interest, is consistent with the knowledge at hand. And the necessity is 1 minus the possibility of the complementary events, so here and here. So you can, so basically it's this quantity. The necessity indicates to what extent event A is necessarily implied by the possibility, by the information you have at hand. So if you, just for those who are interested, a few relations to complete mathematically. What is important is when you make the union of two events, the possibility is the maximum of the possibility of each event, which is quite intuitive. And more important for the rest of our presentation, you have some connections between possibility theory and probability, standard probabilities, and these connections goes through goes through the concept of imprecise probabilities. So a few works have been done to explore the connections and measures of consistency between probability measure and a possibility measure have been found or developed. And we will choose one of them because it's convenient for what we want to do, which is that probability measure P and the possibility measure pi are consistent if the probability measure is bounded between the necessity and the possibility for any event A possible on your set of events, on your set of possible. On your universe, basically. So that's a very important relation because we will use to make parallels, and so I will show you later. So to complete a visual representation of that, so the NP diagram here. So when you have an event A of interest about the state of the system, and you want to quantify, to make a prediction about this event, like will it happen or not happen, and so you characterize the knowledge you have about this event by a possibility, pi of A, and a necessity, n of A, as we've seen before. And then you can locate the points in this 2D diagram corresponding to these two measures. So first, all these areas are inconsistent because of the principles, derivations based on the principles we've been before. You can only have points on the n equals 0 axis or on the pi equal 1 axis. So if the n of A equal 1, it means that your event A is absolutely certain. If n of A is between 0 and 1, it means so you are on this axis and you have you make a tentative acceptance of A to a degree of confidence n of A. And finally, if pi of A equal pi of the complementary event of A, so basically the possibility of the event of interest and its complement are the same and are equal to 1, then it means that none of them is necessary and you are in this at this point, which is totally you are totally ignorant about the future state of the system. And here, so it's a parallel of what we said before here. So it's a tentative acceptance of the complementary event to a degree. Yeah. So, there is a F missing here. So now, how do you build a possibility distribution when you have data? Because, say, for instance, you have a few samples x from x1 to xn about a variable of interest x, and you want to draw a possibility distribution from that. How do you do? So we will use the methodology from Masson and Deneux, which is a methodology that allows you especially to take into account the uncertainty due to the limited sampling, to the limited number of data you have at hand, because we have other methodologies that are more direct, a bit less computationally complex, but that do not take as well into account the uncertainty due to the limited sampling. So you consider a variable similarly defined on a universe, blah, blah, and you bin into n disjoint classes u x-axis. So that's the first step. And you assume that the data has been randomly generated from an unknown probability distribution. So you will try to find the simultaneous confidence intervals on the n probabilities, and you try to have not the you don't try to find the precise simultaneous probabilities, but you try to find simultaneous confidence intervals on these n probabilities. So to that purpose, you can use two models: the imprecise Dirichlet model of Rayleigh, or developed by Rayleigh, or the Goodman formulation. The Goodman formulation will allow you to set a confidence level 1 minus alpha, while the imprecise Dirichlet model is more subjective. So from these confidence intervals, and also the relationship between possibility and probability that we've seen before, the procedure will allow you to compute a possibility distribution that will dominate with confidence 1 minus alpha. So that's in the Goodman case. In the Goodman case, which has which comes with guarantees. So this possibility distribution will dominate with confidence 1 minus alpha, the true probability distribution over the future state of the system. So just an additional word about the fact that these two models to derive possibility distributions from multinomial proportions do not provide the same guarantees, and they are differently useful. We will see it later. And in practice, so that's an example. So here I sampled, so n, I took n samples from a standard normal variable. So from 25, 50, 250, and 1000 samples from the same standard variable, standard normal variable. So in black, you can see the basic histogram of the sampling. And in red, you see the possibility distributions derived from the Goodman model with different confidence level, so 0.90, 0.95, and 0.99. And in so the lighter red, the higher the confidence level. And with in blue, you can see the same possibility distribution computed with the Welle model with different values for the parameter. These are values that are commonly discussed in the literature about this kind of models. So you see, so yeah, that's the conclusion is that overall the Goodman's possibility distribution are much more conservative. But they also come with more guarantees than the possibility distributions derived from the Welle model. But when you increase the number of samples, of course, both converge, and in the end, there is no difference. Yeah, that's what I say here. What is important is when you have less peaked possibilities distribution, and especially when you have basis levels like this, basis possibility distribution level, it means that you account better for the limited size samplings from this relation, because you can derive that the necessity of any event A on this axis will be below 1 minus beta, where beta is the basis level of your possibility distribution. Yeah. And it means that A cannot be accepted at a degree above 1 minus beta. So that's how you interpret this more or less conservative possibility distribution. So now our methodological framework, because we will come back to whether things. Yeah, first let's describe just what do we have at hand to make a prediction. So we will take the monovariate perspective, so we consider just one variable, and we will call truth verification or observation the true state of the systems. This is the jargon of the weather forecasting. And so what do we have at hand when you want to make a prediction, and what are we going to work with? So we have the set of M predictions, so the ensemble prediction system for lead time T. So this is it. We have also an archive A containing n pair of this EPS and the verification for the lead time T of interest. And we have a time series of past observation of X that contains the initial conditions of the prediction of interest. So we will, everything that you will see from now on is based on experiments made on the surrogate model of the atmospheric dynamic systems, so the L. Lorentz 96 systems. And we reproduce an imperfect version of the model. So this is a perfect model here. So where you have X, which are slow moving global variables, and Y are quick, faster changing, more local variables. And this is a surrogate model of the atmospheric dynamics. So this is the equation for the perfect model. So it's deterministic. And in the imperfect model, which we use to reproduce well, an imperfect model as we have in weather forecasting. So we replace this term by this polynomial. So this is a very documented thing. I didn't invented it. and then you sample the initial members. So you create the ensemble predictions and the initial conditions of the ensemble predictions by just sampling n random initial perturbations around each true value of the system. And you evolve them forward by means of this model with the imperfect term here. So the framework now, I'll just take the time. Oh yeah. So the framework. So we will, this is a synthetic picture of the framework. So we will use two sources of information as you've seen in the information at hand. On one side, we have numerical weather model predictions, and on the other side, we will use information about the system. We will try to use information about the system dynamics. So in one case, it's the archive I, in the other case, it's the time series AI. So we will use this archive to, from the analog method and the transformation to create possibility distributions that I showed you before. So in both cases, we will derive possibility distributions for the future system state, so x of t, knowing, so here it's the EPS and the archive of the EPS, and here it's the initial conditions of your system in a reconstructed phase space. I will develop that more later, and the time series of the system, of the variable of interest. And then we will combine these two possibility distributions that are two representations of the knowledge about the system state with a fuzzy intersection. And we will see how it works and what we can get from there. So the analog method, or the more generally, we can say similarity-based method. So in weather, generally speaking, and especially in weather forecasting, analog-based methods are techniques where the current state of the system, so the red point, is compared to an archive of the states taken by the, rather, it needs to be deterministic, else it doesn't work really, to determine the most similar states in the past. So, for instance, my current system, my system at the time t0, when I want to know about the future state of the system, is in red. And I found in the archive that there were like these 5 points, 5 blue points, who were similar, quite close in a reconstructed phase space. So the critical point is what is this phase space? I mean, you have to choose it carefully. So I will use them as analogs. I will say, okay, they are close, the system is deterministic, so they will probably all evolve a bit similarly. And so you make them all, well, you use their evolution in your archive because you have recorded them already. And then you will use the future points, well, their evolved points, as a proxy, as information, as analogs compared to the future state of the system you want to predict. And so we will call these points, these evolutions, analogs as well. So the crucial point is obviously to choose carefully the system in which you assess the similarity between your initial condition and initial conditions in the past in your archive. So we will. So this is a general method, and we will use it in different ways to the EPS information and to the dynamical information. So first, the EPS information. So we consider, because both system and model are to a large extent actually deterministic and close to stationary. So the past behavior of the coupled system model is representative of its future behavior. Consequently, if we are able to enumerate the possible values seen in the archive or not, that's the point of imprecise possibility theory. For the verification X associated with a small range of the values taken by model predictions, then a future observation X should belong to that set of possible values when a future ensemble prediction falls in the same set as X. so that's the idea of the analog method. And you could say, well, but we have perturbed stochastically the initial conditions, so it's not exactly the same model behavior, and we have the model can be also stochastically parameterized in more general weather applications. So what do you do with that? But precisely this stochastic component is accounted for in the assumption of the methodology deriving possibility distributions. So now I just show quickly, I check the time, sorry. Yeah, the methodology to draw possibility distribution from there. So again, you bin your axis of interest with the precision you want. For each bin of your axis, you will, for each bin of your axis occupied by at least one ensemble prediction. You will find the corresponding observations in the archive of archive of EPS and observation, and you will get a set of pseudo-analogs like this. And from this pseudo-analog, you can draw a possibility distribution. So the possibility distribution for the system state, knowing that an ensemble member falls in, for instance, this bin. And so that's what is done in this first plot, and in this second plot at different lead time. So it has 3 days ahead and 7 days ahead. For prediction 3 days ahead and prediction 7 days ahead. And so you see, so here it's quite, it's not a long lead time in terms of prediction. So all the ensemble predictions are quite close. So in fact, you have just three bins that are occupied by ensemble members. We just need one ensemble member in a bin to draw a possibility distribution. If there are more, it's fine. If there are, but one or more will lead to the same possibility distribution. And then what do? Each possibility distribution provides the possibilities for the verification X given the presence of one or more ensemble members in the bin. So each one is a partial view of the state X. And because there is only one truth for the system, we decide to combine them with a union, because each individual possibility distribution is what is possible given the little bit of information we have. So we make a union of this possibility distribution. So we take the envelope basically here. So of course, you can see it quite easily. The possibility distribution, especially at large lead times, the resulting black line, will become very wide. So there is not much information to be gained about the future state of the system. So that's why we will take dynamical information into account, because we have never taken into account the initial conditions so far. So it was obviously too conservative. So we will do the same, so use an analog-based method to find the dynamical analogs of the system from this time series that contains the initial condition. And so you use a similarity-based approach, so exactly like what we've seen here. So this time, because we are talking about dynamics, either you do some attractor reconstruction when the dimension of the system is not too high. So that's what have been done here, and it's based on my system. So of course the system has more dimensions, but I can just show it in 3 dimensions. So you use delay embedding, the delay embedding Takens theorem, and you can reconstruct attractor like this. It's not the point of this presentation, so I'm not going too much into detail, but see if the dimensionality of the system is too high, then you can use a downscaling method, so where some global variables, you will take similarity measures on predictory variables that are global variables, for instance, the pressure, the wind, at synoptic conditions. And from there, when 2 synoptic conditions are similar, it means that local conditions, for instance, about the rain in such valley, will be similar. So that's a way of doing, but well, in any case, the idea is to be able to gain some dynamical information through analog-based predictions. You reconstruct the attractor, or you downscale how you can based on the information and the dimension of the system. But you in the end, you get analog-based predictions from your dynamical system reconstruction, and you will draw a possibility distribution from this analog prediction set, so pi of A prime. And so depending on the value of A of pi of n of A, sorry, of course you will observe different possibility distributions, so they all converge. So I increased from gray, so it was NA equal 10, to here we have in blue NA equal 500, sorry. So 10, 50, 100. So you see that they all converge. And also what you can see is that when you increase the number of analog, you decrease the basis level of the possibility distribution. So you increase the confidence level on basically this area. So is it an artifact of the construction, or is it actually useful, or is it actually, does it conserve all the information of the possibility of observing, for instance, an event here? So we will see it, we will confirm it later in operational forecasting and the operational use of this possibility distribution. So these were plots just to illustrate the attractor reconstruction method here. So where you had a system with a 9 dimension and so on. But that's not really the point of the presentation. So now, if you remember this scheme, we have two possibility distributions, one based on the ensemble prediction system information and one based on the dynamical information. So we will combine them. So that's here. There are two views on the actual system state. They are supposed to account for this. Can you hear me? Yeah. They are supposed to account for uncertainty, but because the source of information was imperfect, they are possibly too conservative. So we will combine them in an AND manner this time, so an intersection, which we think should alleviate their respective over-conservatism. So we use this formula in the theory to compute intersections. And so here is the representation for different lead times. So 1 day ahead, 3 days, 5 days, and 7 days. In yellow, you have the possibility distribution based on the dynamical information. In blue, the possibility distribution based on the EPS information. In blue dots, the EPS number, and in red, the actual truth. And so you see that for small lead time, basically, it doesn't change a lot. You will just take the more peak, like the inside possibility distribution. But then, especially when they are superimposed, when one contains the other, you just take the narrower one. Of course, it changes if one was very shifted compared to the other. But then for larger lead time, you start to see the interest because it will allow to take the intersection and to draw something more narrow based on your two initial possibility distribution. So, okay, now we have a possibility distribution for the future state of the X of your variable of interest. So you will extract the two measures of possibility and necessity of your event A of interest. So we are in a binary point of view. Then how do you do predictions? So either you use it, so that's the fuzzy way, with the indicator called credibility. So it's an aggregation of n and pi, so just the mean. Then you can use for validation score of your prediction, or just to make predictions. Sorry, I missed the word. So the ROC and precision recall curves, which are traditional ways of assessing the skill of a prediction. You can use correlation coefficient, mutual information, or you use these relationships between the actual probability and the possibility measures, and from there you can assess the validity of your predictions with probabilistic scale scores used in probabilistic forecasting. So, namely the reliability diagram, the log likelihood score, or the ignorance score, and so on. So, experimental. Okay. So we will now test this framework on an extreme event. This one we will use for comparison with a probabilistic approach a classical probabilistic Gaussian kernel dressing. So where in fact to infer a probability distribution from your n ensemble members, you just make a sum of n Gaussians fitted on each ensemble member, possibly shifted and scaled. So you have 3 parameters to A, omega, and sigma. 3 parameters to optimize, and to optimize you use the log likelihood score, where x star is your actual observation. So you try to optimize this score, so the sum of the logarithm of the probability from here, yeah, it should be a small p, from here of observing your what was actually observed. And well, we will use 3 verification scores. So the precision recall curve first for estimating the discrimination capability of our method, reliability diagram to estimate the probabilistic calibration, and correlation coefficients. So results now. So first, we said we had a quick discussion about the number of analogs NA. You saw how it influence. It can change, shift a bit towards the bottom, the basis level of the dynamical possibility distribution. So here we draw the precision recall curve. So the recall is the hit rate. So basically, I think, the recall hit rate is the number of your predictions that you of event A as the event of interest that you correctly predict. So in my case, the number of extreme events that I correctly predict over the total number of extreme events observed, and the precision here is the number of extreme event correctly predicted over the total number of extreme event predicted. So basically, the lower your precision, the higher the false alarm rate. So that's what you have to remember. So, but what we can see is that when you increase, so with this level of gray, more the number of analogs that you use to derive your possibility distribution. So you have a peer precision recall curves that will converge quite quickly, and so even though we integrate more distance analogs, this additional information is not used in terms of density as a probability density function would do, because then it would dilute the information given by the closest analogs, especially in an area where you don't have a lot of points in your phase space. So yeah, the possibilistic interpretation of the analog set is preserved. So now, what is more interesting? So it's the general results. So in blue, again, you have the curves connected to the EPS-based possibility distribution. In yellow, to the dynamical-based possibility distribution. In black, to their combination, and in red, the the performance of the probabilistic approach, like the kernel tracing I described before. So this is for 1 day ahead, 3 days ahead, 5 days ahead, and 7 days ahead. So what we can see is that for small lead time, the EPS-based possibility distributions perform just like the possibility distributions. So I just put a line in between, but the points are on the same curve. So it performs similarly because in fact there is no model error. So well, I will come later. Then when model error, when the aggregated model error becomes more important for intermediate and larger lead time, the possibility, the EPS-based possibility distribution works better than the probabilistic approach. And also you can see that the yellow line starts to work better and better. And the combination of these two sources of information will work better and the end better than the best source of information. And so that's it shows that for small lead time, for small bit rate especially, this approach can perform better, provide less false alarms than the probabilistic approach. And in any case, we can work. We have similar performances based on the EPS possibility distribution for small lead time. So that's what is summarized here, and what a small explanation, a small insight comes from this three-dimensional possibility diagram. So so this is a possibility diagram in this plane, and we represent an histogram, so the number of predictions when conditional to the observation of the extreme event from each possibility distribution. So attractor, so dynamical in yellow, blue for the EPS, and black for the combine. And what you see is that the attractor from start has a peak on the ignorance, because the attractor-based distribution, the dynamical-based distribution, is quite wide. That's why you have very poor performance here. But while the EPS is better for small lead time, so you are close to the certainty. But then with growing lead time, the EPS start to be more on the ignorance side point as well. And you see that the combined possibility distribution is still below both, because the synergy between the EPS-based and the dynamical-based information will allow to provide more information than just each of them provides, and more predictive information. So we confirm this observation with an estimation of the correlation between the prediction. So in the possibilistic setting, it's given by the credibility indicator we've seen before. And the categorical variable that we predict. So it's based on a logistic fit to have a nonlinear correlation assessment between these predictors and the categorical variable. So the higher the level of the deviance of the logistic fit, the lower the correlation. So we want lower correlation. And so you see that the probabilistic approach here performs less well than our EPS-based and for intermediate and large lead time, our combined approach. And you can also see here, it's when you do a possibilistic, when we assess the correlation of the multivariate variable composed of the probabilistic predictor and the possibilistic predictor. And we see that it's a bit below the possibilistic predictor, which means that we could combine the probabilistic and the possibilistic information and maybe get better results, get better predictive results. Now, reliability, which was one of the key points of the limitations for the probabilistic approach. So we use this formula. So from our possibility and necessity measures, we derive a probability just using this formula, because we know that the probability is bounded between both possibility and necessity. And for each alpha varying between 0 and 1, we can, like this yellow line, for instance, it's alpha equals 0.9, we can do a reliability plot. So the closer to this diagonal, the more reliable the probabilities, the predicted probabilities. So the red is for the standard probabilistic approach, and the black lines are the bounds when we compute this and plot the reliability diagram for all alpha between 0 and 1. So the black line corresponds to alpha equal 1, and the lower black line to alpha equals 0. And what we can see first is that with this approach, with our approach, we can provide high probabilities for the observation of an extreme event, while for large times, while the standard probabilistic approach just cannot. They can never issue a probability above 0.5 when it comes to the observation of the extreme event. And second, for instance, with 0.5, with alpha equals 0.9, we are very close from 0 to 1, so over all the range of probability, to perfect reliability. So here we are for reliability. You can also use 3D reliability diagram. So same, we have our NPI reliability diagram. And in the third dimension, you plot the observed frequency of your extreme event when a prediction falls in this bin, for instance. And so what this diagram allows you, for instance, is to compare, to represent ignorance, because if the probability, if the relative the observed frequency here at the ignorance point was 0.5, it would mean indeed that when I have ignorance, when my possibility distribution says, oh, we are ignorant, it means that, okay, there is a probability of 0.5 to have extreme event. And so it can be either extreme event or a non-extreme event with a 0.5, with a 1/2 chance. But what it shows is that no, it's different. So it addresses the question of how to represent ignorance, and represent it differently from P of A, from probability of A equals 0.5. And especially when we have here at the ignorance point an observed frequency that is different from the climatological frequency of your extreme events, so it's normal distribution in the set, you can wonder if it can show that there is a failure in the structural deficiency in the model to predict A. So, and you can use these frequencies, observed frequency, to propagate uncertainty in applications of your possibilistic predictions. And just a last word about the guarantees. So here, the colors refer to different methods to derive possibility distributions. And you can see the distribution of the measure pi of A and n of A for all the colors, but red, it's when you observed A, so when you observe the extreme event, and the red correspond to observed non-extreme events. And what you can see is that the possibilistic methodology guarantees that the possibility of A is above 0, so you can show it analytically when A is observed, so it's useful for risk-averse decision makers. But it's not useful to take decisions because in an economical world. So the AND combination is designed to increase the upper bound on the necessity, which will help you to make decision making, more efficient decision making. Well, just to have trade-offs. And overall, less conservative methods, so these ones, take more risks, so you have more peak distributions, and on the long term, they provide more reliable associated probabilities in terms of distribution on the Empire 3D diagram for larger lead times. And just in a word about the effect of the size of the archive. So possibility theory is precisely used to account for the incompleteness of knowledge, so it maintains the guarantees I've discussed before, even when the archives are very small. Of course, it's at the expense of the predictive skill, so namely the discrimination. And to conclude, so well, I just say again what I've said in this presentation, but we can combine with this framework several incomplete sources of knowledge in a consistent manner, which allows to reduce their respective conservatism. So we create a synergy, we extract more information, and we create a framework that is more direct than the probabilistic one, because we will never try to correct misleading EPS-based probabilities from start. Our possibilistic interpretation makes sense. And we reproduce so the probabilistic predictive skills at small lead times for an extreme event. And finally, this framework has is interesting in terms of explanatory power, because we take the uncertainty into account, the uncertainty on the probability. We can have both interpretation, a non-frequentist interpretation of the result and a frequentist interpretation of the result. And to come back to our initial questions, there is indeed more predictive information and explanatory power to be gained from an imprecise probability framework at large lead times, when the aggregating model error starts to be significant. And we chose possibility theory because for its intuitive rationale, and also in terms of communication, it's quite interesting. So here it is. If you have additional question, well, just let me know. I don't know if you're still here.
Right. Thank you, Noémie. If people have questions, you can raise your hand in the participants menu. Otherwise, yeah, thank you very much. Anyone got any questions, Dra? Yeah, Adolphus, you've got a question.
Yeah, so it's just a very short question. It's mainly on a just out of curiosity, because I'm unfamiliar with something that you explained earlier. So I think Noémie, is regarding the slide whereby you talk about the where you introduce the possibility theory. I can't remember which one, where you have this box and you talk about you know, ignorance is when n equals to 1, and it's one of the earlier slides.
Yeah, I just try to reshare it.
Sure.
So, okay.
So can you share the screen as well?
Yeah, I just try to reshare it. Okay. So do you see it? No. Yeah.
No.
Not yet.
We're still seeing you.
Yeah. What did you say to share it, Scott? I can't remember.
Share screen, and then you click the window that has your slide on it.
Are you doing it through Zoom?
Oh, okay. Wait. I will do differently. So sorry. Share screen. It's just you won't see it. Okay. So you see it. It's not perfectly, but you see it. So in the basics. In the basics. So yeah, which one?
Down. Go down. I mean, the next slide.
This one?
No, the next slide. Yes, this is the one. Sorry, 12. All right. So I'm still a little bit confused, because you mentioned that ignorance is when, I believe, when pi a and pi a complement equals to 1 and n a equals to n a equals to 0. Could you like re-elaborate this part about ignorance again, because I'm still a little bit confused because I'm quite new to this, so I'm just wanting like if you could reiterate, like, you know, because I got a bit confused as to like what pi a and pi a complement represent, and n a and n a complement represent, to give you the ignorance.
Well, to be honest, the connection was poor, so I haven't understood everything. So you want to understand more what ignorance is, and that it?
Yeah, something like how do we get to this interpretation of ignorance?
Oh, well, I will come back to this one.
Okay.
Okay. So it's a little bit like I think it's a question of causality. So, okay, because your system must be in one state, so it's either A or not A. So, so in fact, the possibility is the maximum, the possibility of being in A, so it's given by the maximum here, and the necessity is given by how possible is the complementary, by the complementary of how possible is the complementary event, because the more your complementary event is possible, the less necessary is your own event, your event of interest. So that's why that's how possibility necessary and ignorance are related because yeah, if both events are possible, like fully possible to one, you are in total ignorance because you cannot favor one over the other. Is that
right? Yeah, okay, that sort of like clear the doubt. Yeah, thank you so much for your explanation, Naomi.
You're welcome.
Right, thank you. Alex, you have a question.
Yeah, it was just I don't know if this just went over my head completely. On slide 19, you talk about some sort of similarity metric that's used to pick out the time series in the archive that you're using.
Yeah.
Did you explain what that similarity metric was?
Yeah. Oh yeah. Sorry.
Yeah. Sorry. Go on.
Oh no. Continue your question.
No,
Sorry.
just how just what you're using to determine the similarity between the observed time series and the time series in the archives.
Yeah. So well, I try to generalize under the name analog method or similarity based method this idea that if initial conditions are close for deterministic system, well, the evolution will be close. So, but I apply it differently. But the idea is okay. How do you define? So, of course, you have question of metrics, but the metric here is often just a Euclidean distance. So there is nothing special. The more important thing is which variables of your system, because it's not just the distance between your variable of interest, because we are in a univariate case. So it's not just the distance between the variable at your current initial time and what was in the possible instance of the archive. No, it's you will create a vector of explanatory variables based on either just your time series of the variate of interest. So that's the idea of the delay embedding, for instance, where in fact, so it's just x, my variable of interest, but I will find a dimension m and a delay tau, so that I can express, I can have vectors xt minus tau, xt minus 2 tau, and so on till till like this. So these are delay embedded vectors. So it's just based on the time series of the variable of interest, but it will reveal the dynamical structure of the system. And in this structure, in this new phase space, I can just use my Euclidean distance to say, okay, 2 points are close or not close. Now, if you are not able to do delay embedding like this, maybe you use just different set of variables. So not only these variables, but maybe other variables connected to your system of interest. And you will say, because it provides more information than just my variable, when all these variables are close, like when my initial conditions in terms of this set of variables is close to another point in the archive with the same variables, well, and close again in terms of Euclidean distance, for instance, or you can use other distance metrics, but I haven't looked for that, to be honest. And yeah, I think the Euclidean distance in this application is what we need. So you see the idea more?
Yeah, so you're trying to look for a subset of the variables that have like the most predictive capacity, and just reduce it to just looking at the set of histories that have those similar variables, and taking that with the Euclidean distance and using that as the set of
Yeah, that's it. It just the idea is just that because we are in a univariate perspective, X doesn't have enough information just to take the similar X in the past. So you will build higher dimensional vectors, and so either from attractor reconstruction or by adding additional variables. That's, for instance, in downscaling, statistical downscaling method in weather forecasting, that's what they do to predict the rain in a valley. They will say, in a local event, they will say that when you have synoptic conditions, so large scale atmospheric circulation conditions that are a bit similar, you have basically more chance to have the similar thing happening as in the past in your valley or in your whatever. So yeah.
Okay, thank you very much.
Welcome.
Yeah. If anyone's got more questions, I've got some time.
I don't know how to raise my hand on this. This is very confusing for all.
Because you're the host.
I think if you're a host, you're unable to.
Ah, okay. Which makes it naturally impolite. On Noémie, on slide, I think it's 21.
Mm-hmm.
What are you enveloping in slide 21? What are those exactly?
Yeah, so it's connected to the previous question as well. So here I use the analog method in a different perspective. So it's I say, okay, my ensemble, I have an ensemble prediction. So one of the blue dots in a bin here. So here in my case study, I have 30 bins. So it's because this is supposed to be like a weather variable. So it could be like temperature. So I say if I partition it into 30 bins, it means that I have a 1 to 2 degrees resolutions. So it's quite good. So basically, if I have one blue dot, so for instance here, one blue dot in a small bin, I will look in the archive for all the EPS, for all the observations, the actual observation connected to an EPS member falling in the same bin at the same lead time. And this analogs, so the corresponding observations, are a set of analogs, and I will use them as the raw data to draw a possibility distribution. So it will correspond to the possibility of having the observation when an EPS member or more are observed in this bin. And so it's one of these things. And so I do the same for all the bins where that are occupied by at least one ensemble member.
So the things that are being enveloped there are possibility distributions that you've created by sort of seeing the data in from different points. Is that the idea? Or not at all?
So yeah, so each possibility distribution, so each not the envelope, but each one of them is creating by just looking at the information provided by ensemble members falling in one bin, in one given bin. But then if our ensemble members fall in 3 different bins, like here, there will be 3 different possibility distribution. And
So
here a lot.
So each one is a possibility distribution.
Yeah, each one is a possibility distribution, and I combine them with an union, and that's how I do the envelope.
Envelope or whatever that is. So am I correct that you used one bin definitions throughout? You just had one bin structure, right?
I have, yeah.
Bins or anything. So my question would be, how different would your results be if you did different bins, if you like got smaller bins, or if you varied there was...
Yeah, to be honest, I have done it. I have done it, and the results were not significantly different. I think it was an optimum number of bin, if I remember correctly. But I have not redo it recently, so I don't want to.
Right.
But I remember that it was increasing the number of bin too much is not good. Well, it's a trade-off with the size of your archive, because if you have too many bins, then you will never find enough analogs in your archive, and then the possibility distribution will be guaranteed and so on for sure, but they will not help you to, they won't be very peaked, and they won't help you to make efficient decisions. So in terms of prediction, you won't have very interesting predictive information.
So you'll be blinding yourself to the information that's there. Is that what you'll be doing? So when you make the bins too big, you know they're too big because you can no longer see any signals at all. Is that
well, if they are too big, no. So that was the case of if they are too small.
Sorry.
Now, if they are too big, well, it can only improve the. No, if they are too big, actually, you improve your prediction, your performance prediction, but till a certain limit, because at some point you don't have resolution. So
enough points. So I guess then that there is some study that would need to be done in each case to figure out what the right bin is, or maybe a strategy to determine, I don't know, bounds on bins or something.
Yeah, sure.
Okay. So and another question is, you said you were using L96, and I guess you're using that as a surrogate, right? You're creating the truth with that with the lens model, right? So obviously, the obvious question is, so what if you used L97 or L95, if such things exist? Would you see a similar story? Or, I mean, I assume you expect to see a similar story, but what, if you used a deterministic model that was not chaotic, would this fail, or would it give a degenerate answer? What should we expect?
Well, it's not a question of being chaotic or not. It's just a question of, I think it can be used with anything, but because...
So work with limit cyclic models then too.
Sorry?
Work with models that are just limit cycles or go to equilibrium.
Well, I would need to see more exactly the application to say something, to be honest. But there is no assumption about chaos and so on. It's just this application is interesting for highly sensitive to initial condition systems because the standard probabilistic approach doesn't work precisely for this reason.
Right, because they're so. Yeah. Okay. Thank you.
Okay. Marco, I think you've got a question.
Hi. Yes, I mean, thanks, Noémie, for the very interesting presentation. Most of my questions have partially already been answered, but in particular, the last question of Scott, I think it's really interesting to see how this can be generalized to a deterministic model. And I think partially you answered that question, so okay. And also I think Tanya has a question about attractors, and I mean, what exactly you mean by that? And is that like the Bayesian of attraction type, or is just a domain of where your deterministic system is stable?
Okay, yeah. So I'm not I'm not familiar. I'm not a specialist either in this domain. So I don't. What is sure is I took okay. My system is is not in the transient regime. So I've been beyond that. And in the assumption of the method, you need to be in a close to stationary regime of the system, dynamical system. So yeah, that's I use the attractor because it fitted well this system and the assumptions. So I use the dynamical attractor for this region. But of course, for a lot of natural systems like weather dynamics and so on, you cannot build such attractors. So that's where you use this statistical downscaling I've mentioned. So you use a similar, like similarity-based, analog-based method. It's not based on a dynamical attractor reconstruction. It was convenient for me, but I don't pretend to generalize it to any kind of system.
Oh,
I don't know if it answers a bit.
yes.
But in this context, what does the attractor means? I mean, it's like where the system is chaotic, where the system, where the chaos takes place, or what does, because for me, it's not really clear what attractor, where,
okay.
How do you define this attractor?
Okay, so yeah, here. So I just okay. So I use this model with the parameters that are standardly used when in this surrogate model used for atmospheric dynamics prediction. Okay, and I use the Tekens delay embedding theorem to reconstruct a phase space where I could see, a structure like the underlying, the structure governing the underlying dynamics, and I used here. So some methodology. It's the empirical dynamical modeling. So it's a global methodology of attractor reconstruction made by someone dealing with ecological systems and also weather forecasting. Mostly ecological systems. So to estimate the parameters of this attractor reconstruction. So that's how I did. So the only thing I can tell you is we are beyond the transient time, so we are in a stationary system, stationary regime dynamics. But I cannot tell more about I have no idea more about these things.
Okay, yes, thank you.
Alex, do you have a question?
Sorry, no, I think I just didn't put my hand down.
Okay, sure. Fine. I just need to add that I think there are some Ezreal talks beginning soon, and I think you need to register for them if you want to join. There's a link in the chat near the beginning if you scroll up. But yeah, if there are any further questions, then we can conclude this talk. Right. Thank you, Noémie, for your talk.
Thank you
I'll
very
stop.
much to follow this.
Naomi, it was a really, really interesting talk. So thank you so much. Yeah. Merci beaucoup.
De rien.